Hello everyone, we are going to start Chapter 7, Section 1 today. We're going to get through part of it, starting off our compound nomenclature, and we're going to start with Ionic nomenclature. I asked you as part of your homework to get a lot of ions written down. You had monatomic and polyatomic ions. I want to make sure that we're on the same page and you have those handy as you go through your lesson today. So this right here is a picture of your monatomic ions. If you want to label those, monatomic ions. And again, mono means one, so these are going to be individual elements and what their charges are. Hopefully, if you've already looked at these, you notice a few things. These right here are your group 1 elements. They all have a +1 charge. In the next spot, we've got our group 2 elements, all with a +2 charge. And then next to that is aluminum. It's in group 13 with a +3 charge. Hopefully you remember this stuff from Chemistry 1. And then below that, everything with a -1 charge. That is group 17, which is the common charge for it. If it has a -2 charge, that is going to be group 16. And then next to it, a -3 charge, that is group 15. So those ions at the top, those ions, that is going to be their most common charge. If you're talking about a group 1 or a group 2 metal, that is their only possible charge. And for fluorine, fluorine's only possible charge is a -1. So we do have some exceptions, but we'll get to in a little bit when we start talking oxidation numbers. At the bottom for our monatomic ions, these are going to be your D block metals and a few of your P block metals. Those have more than one, most of them have more than one common charge. As you're looking these over, just to highlight a couple, I see vanadium. I see a vanadium +2, +3, +4, and those Roman numerals, you'll see me abbreviate Roman numerals with RN. The Roman numerals indicate the charge. So if it's Roman numeral 2, it will have a 2+ charge. Roman numeral 4 will have a 4+ charge. Any of them with Roman numerals means that element has more than one possible charge. On this particular page, though, it just lists the common ones. As I'm looking at this, I see, let me find one. How about manganese? Manganese, Roman numeral 2, means it has a 2+ charge. I don't see it listed anywhere else on this paper, but it just means manganese, Roman numeral 2 is the most common charge for manganese, but there are other options. Now, if these metals do not have a Roman numeral, and we've got some that we will highlight, such as silver, zinc, cadmium, aluminum is a metal, but it's up there at the top in group 13. Those metals are saying, hey, if I don't have a Roman numeral, that's going to be the only charge that either is possible or that we are even going to consider. So silver, zinc, cadmium, aluminum, all of those, that's their only charge. Why don't you look at your periodic table and look at the location of silver, zinc, cadmium, and aluminum? You'll notice that they are all very close together within the periodic table. And that also has to do with some of their properties and then what you see there. So these are your monatomic ions. Let's move on over to polyatomic. So looking at these are our polyatomic ions. Poly means many. So we just have multiple elements in most cases put together. You need to get used to these, using them. The big thing, hopefully, that you've noticed already is the ending. A lot of these end in ate or ite. So they end in ate or ite. Those are going to also have oxygen associated with them too within their formulas. We've got a couple that we're going to concentrate on, especially the ammonium that has a +1 charge. The rest of them have a negative charge of 1, 2, or 3. And if I were to look at these, just so that when we start doing our formulas, for instance, I see dichromate, Cr2O7. For now, until you get good at it, get used to putting parentheses around that part and labeling the charge on the outside of the parentheses. When we start moving that charge of a 2 for the 2 minus around to make us some neutral compounds, it's going to be important that that subscripted 2 and subscripted 7 do not move. So for now, add those parentheses until you get good at working with some of the rules that you're going to learn today. So these are our polyatomic ions. There is a special situation for our 8s and our ites, and you'll get to cover that during your homework. So moving on with ionic nomenclature, that's what we're going to concentrate on in this particular video. And for our ionic formulas, you're going to write each ion. The cation is first. As a reminder, cations have a positive charge. The T looks like a plus sign. So cations have a positive charge, but we don't ever show charges, those pluses and minuses, in our final formula. The overall charge must be equal to 0. I will show you how to do this. In most cases, we're going to do something called the crossover method. So the crossover method to get those charges to cancel. If your charges are opposite, meaning a +1 and -1, or a +2 -2, those charges cancel. We just write down the symbols. But if not, we're going to use subscripts. Subscripts are the lower numbers to balance our charges. And again, like I was showing you earlier, use parentheses around polyatomic ions. You have to if there's more than one, and hopefully you're going to get good at that. So parentheses around polyatomic ions. And those Roman numerals we were looking at, it goes with a system called the stock system. And Roman numerals indicate charge. So when we saw a Roman numeral 2 listed, that meant it had a +2 charge. If it's a Roman numeral 4, then it has a +4 charge. For our class, we are not going to work with Roman numerals. For covalently bonded compounds, we're going to stick with the ionic, keeping it somewhat simple there. And Roman numerals are only going to go with your metals. Metals only. Metals only, and not all metals need Roman numerals. Again, group 1 metals, never. Group 2 metals, never. Their charges are always +1 and +2 respectively. Now moving on to ionic names. You're going to write the names of both ions. Again, the cation comes first. I won't ever, whether it's a worksheet, homework, in class, I won't ever give you the cation and anion backwards. Whether it's the name or a formula, it's going to be given to you in the proper order. If you have a monatomic ion, the ending changes to "-ide". Monatomic ions, the ending changes to "-ide". Those ions are typically your anions. Anions have a negative charge. So if you go back and look at your page of monatomic ions, look at those in the middle, your -1, -2, -3 charges. Notice the ending is always "-ide". I see fluoride, chloride, oxide, nitride. So they have changed the ending of those monatomic anions to "-ide" for you. Polyatomic ions all have special names. So again, you can go look at your polyatomic ions. Lots of special names. Most of them end in "-ate" or "-ite", but there are going to be a handful of exceptions on that list that end with "-ide", IDE, but they are polyatomic. And again, the stock system, we're going to use Roman numerals if it is a metal that has more than one possible charge. So again, Roman numerals go with metals that have more than one possible charge. Again, I'm looking at my monatomic ions. Some examples: vanadium 2, 3, and 4, chromium 2 and 3, lead 2 and 4, iron 2 and 3. Hopefully you get the idea. But again, those mean those metals have more than one option. Other things to consider. As you're going from names to formulas or formulas back to names, is there a polyatomic ion? Well, typically if you only have 2 elements in your formula, the answer is no, the majority of the time. If the ending of the name is "ide," typically the answer is no. But again, we had some polyatomic ions that ended with "ide," such as cyanide or hydroxide. But in the latter part down here, if the name ends in "ate" or "ite," it is guaranteed to have a polyatomic ion. And if you have 3 or more elements for what we're doing, absolutely there is a polyatomic ion. Then you also have to ask yourself, hey, does it contain a Roman numeral? Either it does if it's a name, or maybe it doesn't. So does that metal need a Roman numeral? And this last part won't make just a whole lot of sense to you just yet, the no prefixes. But when we get into molecular nomenclature, the prefixes are everywhere. We're not using any set prefixes for you within ionic nomenclature unless it's one that's already part of that given name for a polyatomic ion. And this is just a reminder of common ion charges that you should have already learned or hopefully remember. If it is group 1, the common charge is a +1. If you recall, it had to do with number of valence electrons. Group 1 has 1 valence electron. They like to lose it. Group 2 is a +2. Again, they had 2 valence electrons. They're going to lose those 2. Group 13 is a +3. Group 14, we say Na because, again, 4 valence electrons. They're either going to gain 4 or lose 4 typically. So it's kind of on the fence. Group 15, though, is a -3 because they have 5 valence electrons. They would add 3 more to that to get to their happy 8. So -3 charge for group 15, -2 for group 16, -1 for group 17, and then group 18 we're given a 0. So again, you should have already had your common ion charges, talked about that. If you have any questions, let me know. Now let's get to a little bit of practice. We're going to work through some pretty easy examples that are here on the PowerPoint, and then I'll add a couple more that are going to be a little harder to get you to think. First off, potassium chloride. I want you looking at that ion sheet that you've got, and the first thing you need to do is write down the symbol and charge for each of the elements that are listed. So for potassium, it is K+, chloride Cl-. I noticed that those charges cancel. A 1+ and a 1- cancel each other. Your final answer is KCl. Easy. Next up, magnesium nitrate. Magnesium, Mg2+. Nitrate is NO3. That's a polyatomic ion because I noticed the 8. Its charge is a 1-, but again, put those parentheses around it so we can get used to where our numbers go and we don't lose anything along the way. 2+, 1- do not cancel. So this is where the crossover method comes in. And for crossover, we're taking the 2, crossing it over here. We're going to take the understood 1 and cross it right there. 1s in formulas are understood, so you do not have to rewrite that. And our final answer, Mg, the 1 would go behind it subscripted, but it's understood. NO3, that 2 has to come over behind it. You would not leave your answer like this because it looks like 32 oxygen atoms. You have to have that parentheses right there. That way it's 2 nitrate ions. 2 nitrate ions. For now, if in doubt, put the parentheses around polyatomic ions every single time. I will not count off even if they are not necessary. And then in this last example, copper. The symbol is Cu. The Roman numeral 2 has to be a 2+, plus because it's a metal. Chloride, Cl-. Again, those charges do not cancel. So when we look at crossover, The 2 will come over behind the Cl. The understood 1 right over to there. And our final answer, Cu, understood 1, Cl2. Notice in my final answers here, no pluses or minuses, and no superscripted numbers, so numbers up high, no pluses or minuses, and again, only subscripted numbers. Let's add one that's going to be a little bit harder. We're going to get you to think. Let's go through lead, Roman numeral 4, chromate. So I've got all kinds of stuff going on here. I see a Roman numeral. I see that ATE ending, meaning I have a polyatomic ion. So let's start with lead. Lead is Pb, and its charge is a 4+ because of the Roman numeral. Chromate, I'm looking off of my sheet. Chromate is CrO4 with a 2- charge. And again, I'm going to throw my parentheses around there. Now, those numbers do not cancel as far as our superscripted charges do not cancel. So we're going to cross them over. The 4 and the 2 cross over. It becomes Pb2, because again, my 2, I want it to cross over. And then we've got our CrO4. The 4 here has to cross over. Got to put those parentheses, though, to cross that 4 over. And again, we don't want it to look like 44 oxygens. We have 4 chromate ions. Now, in all the rules I went over, this one that I'm going to state right now, I did not, so I'm bringing it up now. In an ionic compound, if those charges can reduce to smaller whole numbers, you have to reduce them. In this case, the 2 and the 4, which were my charges, have to reduce to a lower whole number, which is 1 and 2. You do not write the 1. Got to keep this in parentheses, and that changes to a 2. So our final answer for lead 4 chromate is Pb parentheses CrO4 parentheses 2. So add that to your list of many rules we will get to. Now we're going to look at formula to name. Formula to name. You had some rules. Go back and look at that one page that we have that says for ionic names. This first one only has 2 elements. So that means the ending should be "-ide". The name of Na is sodium. Great. The name of Br is bromine. But because it's the anion and it's the second element, we change the ending to "-ide". It is sodium bromide. I go back and I look at my metal and I have to ask myself, is that a metal that needs Roman numerals? Well, sodium's in group 1, so no Roman numerals for it. That's your final answer. In the next one, I see 3 elements, sodium, carbon, and oxygen. Automatically, you have to be thinking polyatomic ion. The majority of those polyatomic ions had negative charges, meaning they have to come at the end of your formula. So I'm going to look at the last 2 elements. CO3. I noticed from my sheet, that is definitely a polyatomic ion. Let's go ahead and kind of separate it out. Its special name of CO3 is carbonate. So I've officially taken care of the last half. And the name of Na is sodium. And again, sodium, group 1 metal, does not need Roman numerals. Sodium carbonate is my final answer. For the next one, FeCl3. Now, when I look at that, I only see 2 elements. That's great. The name of Fe, iron. The name of Cl is chlorine, but because it's the second element, we have to change the ending to ide. So this is going to be chloride, iron chloride. But I look at that metal, it's iron. Iron is in the middle of the periodic table, so the D block probably has Roman numerals. I go back and double check my sheet. Sure enough, iron can be a +2. Iron can be a +3, potentially some other things. So we've got to figure out which Roman numeral it is. Now I'm going to show you something that works about 75% of the time, but then I'm going to show you something that works 100% of the time. Now chances are, whatever that subscript is at the end is the Roman numeral. So we're going to go back and look. Is that Roman numeral really going to be 3 for iron 3 chloride? A lot of times yes, sometimes no. Here is a method that I use that works every single time though. Please write these steps down. I'm going to say them verbally. You write the steps down as we go along. Step number 1. Write a box above your metal. Write a box above your metal. Step number 2. Above your anion, write its common charge. So above the anion, write its common charge. The anion's at the end, that's the chloride ion. Its common charge is -1. It's in group 17. It's also on your sheet. Step number 3. Multiply the common anion charge by the anion's subscript. So multiply the anion charge by the anion's subscript, and you get, in this case, a -3. Step number 4. Since this is a neutral compound, I need the number right here to cancel whatever is under the anion. So what do you add to a -3 to get 0 so they cancel? That is going to be a +3. So those two numbers at the bottom need to cancel each other. Next step. This should be step 5. Step 5. I want you to divide the number below the metal by the metal subscript. Right now, our metal iron has no subscript. It's understood 1. So what is 3 divided by 1? It is 3. Ding, ding, ding. That is our answer. Iron, Roman numeral 3, chloride. To me, it kind of looks like the weather pattern. We're making one big circle, but anytime you move down, you multiply. Anytime you move up, you divide. This method becomes very important when we get to oxidation numbers in the next section. So I will go through another example where that reverse crossover, bringing the 3 up, is not going to work, but this method definitely works. Let's go work one out. With this example, we are going to look at, let's see, how about, oh, sorry about that. How about this formula? So if I ask you to write the name for it, I hope right off the bat you realize there's a polyatomic ion. The parentheses should definitely give it away, but there are 3 elements. So let's go ahead and name that special polyatomic ion. I look at my sheet. SO4 is sulfate. And V is vanadium. Now, vanadium, from our sheet, it has all kinds of Roman numeral options. We have to figure out what it's going to be, so let's go back to our steps. Starting again, step 1, put a box above the metal. Whatever number ends up in that metal, above the metal, will be our Roman numeral. Step number 2, what is the anion charge? It's the whole polyatomic ion in this case. That is our anion. Sulfate's charge from your paper is a -2. That's for all of SO4. Number 3, multiply the anion's charge by the anion's subscript. You get a -4. Step number 4, we need to add some number to -4 to get a 0. That's a +4. And step number 5, on the way up, we are going to divide the metal's bottom number of a +4 and the metal subscript. Right now it's an understood 1. So 4 divided by 1 is 4. The Roman numeral is 4. Notice reverse crossover would not have worked in this case because as I look at it right here, the 2 is not what ended up in that box. So reverse crossover would not have worked here. Be aware of that. And let's look at one more example because this is also a common mistake. I'm going to pick a formula that is very similar. VSO4, which is not the same as what you see up there. There is definitely a polyatomic ion. It's the last 2. It's still the sulfate ion, SO4. Still vanadium. We're just going to try to figure out what's the Roman numeral that goes in here. So let's go through our steps again. In your head, be thinking, what Roman numeral do you think is going to go in there? Is it still a 4? Is it a 2? A 3? What's it going to be? So starting off, we put a box above our metal. Step number 2, common anion charge. It's still SO4, so SO4's charge as a whole is -2. Step number 3, we multiply that times the anion's subscript. At this point, most people say -2 times 4 to get a -8, and that's where you mess up. SO4 is its own ion. So technically the subscript is 1 because we have 1 sulfate ion. So -2 times 1 is -2. So put those parentheses, be on the safe side. I do not count off for that. Step number 4, we're going to add a number under the metal to get a 0, so that's a +2. And then step number 5, on the way up, we divide the number under the metal divided by the metal subscript. So 2 divided by 1 is 2. In this example, we are dealing with vanadium 2 sulfate. Vanadium 2 sulfate. So please make sure you have that pattern down pat. It's going to come in handy. You will see that often.